Okay, so it's recording, and welcome to part 2 of lecture 9. We closed the previous session, the lecture 9, part 1, uh, by saying that we are going to announce the postulate 1 of quantum mechanics. So I will just read the postulate with you, and I will explain. Okay. So the quantum state associated to the photon polarization, and here again we are talking about monochromatic light propagating on a fixed direction, is represented by the normalized state vector C, such that if I have a cat C with entry C1 and C2, where C1 and C2 belongs to the complex numbers, then if I compute the scalar product of C with itself, so if I take the Dirac bracket, I will get 1. So this is a postulate, okay? If I'm describing this quantum state associated with light polarization, then the quantum state must be described by a vector with such properties. We are here discussing about photon polarization, but this is a postulate that will be extended to general systems. So if I want to describe quantum states of a different physical system, the quantum state will be described by a vector such that this vector is normalized, okay, with respect to the standard inner product in the vector space that it lives. So I'm going to write down the postulates using the photon polarization as the example, but this is just to be concrete, but this is more general, okay? This is going to be extended for more general systems. Well, there is an observation that is very important, actually, which is the following. The way that you represent the vector state is not unique, okay? And this must not be a surprise, right? I mean, when you describe, for instance, classical systems, you can use different coordinates to describe the system. And you are not changing the system, you're changing the coordinates, which are just labels that you use to describe the system. But of course, I mean, an apple will fall irrespective of the coordinates that you're using, right? So if you want to use Cartesian coordinates, polar coordinates, or whatever, the apple will still fall. So physics will not change if you just change the mathematical representation that you're used to describe it. But of course, it's not true that you can describe a physical system with any type of representations. I mean, you have, for instance, when you're describing classical mechanics and using Newtonian formulation, you have to ensure that you're using an inertial reference frame in order to use the Newton's laws in its canonical form. So if I give you a state and ask you, does this state describe a photon polarization, then the answer is not immediately given just by looking at the vector and recognizing it being cosine theta and sine theta, because I can change the representation of this vector and still describe the polarization of photon. Let me explain that in more details. So to begin with, if I have a state vector, then by definition, by postulate 1, this is a normalized state vector. But now, so let's assume that I have a state vector C. If I multiply this state vector by a phase, namely a complex number of norm 1, I can ask, is this new state, which is the previous state times this phase, describing a different quantum state? The answer is no. So if you take the bra associated with this cat, then you have to write the bra associated to C and take the complex conjugate, right? You remember that you transpose and take the complex conjugate. So you have to take the complex conjugate of e to the I alpha as well, which is e to minus I alpha. And now I can compute the scalar product between this bra and this cat. And when I take the scalar product, I will have the bra multiplying the cat. And you see that this exponential here will cancel against this exponential here. So you come back to bra C times cat C. So you can see that the scalar product between these two states will give the same scalar product between the initial state C. So multiplying by a phase is just a mathematical procedure that you can do. Multiplying a quantum state by a phase is a mathematical procedure that you can do, and you do not change physics with that. In particular, you don't change the normalization of the vector because this phase has norm 1. Okay? So if I give you a state, you can write down, I mean, in quotation marks, a different vector just by multiplying it by a phase. So you're going to look at the vector, and it will be different from the initial vector that I gave to you. But it does not mean that it represents a different quantum state. Okay? So you have to be careful with that, because a quantum state is not uniquely defined. So you have to be sure that you can extract phases, global phases from it, and so on, and go back to the original vector. So Mahmoud is asking, what do I mean by a phase? So a phase, it's what I defined here. So a phase is just a complex number that I can represent as the exponential of I times a real number, theta. This is what I call phase. It's just a name for this type of complex numbers. Okay? Good. But moreover, I can write down a state vector in a different representation with respect to the representation that I used here. And this might be very different from the vector that I started, but the physics that they describe is the same. So you can think of that as having a reference frame in classical mechanics. And once you have a reference frame, you can rotate the reference frame, okay? So you can perform a rotation. Of course, the coordinates of the vector that now you're describing the position of some particle and so on, this will change with respect to the new reference frame, right? So if you look at a vector, the coordinates of a vector in one reference frame, you're going to change the coordinates in the new reference frame, but it doesn't mean that they describe different physics, okay? So there is a question. Is it right to say two states of the scalar problem is one? So if two states, So if you have two vectors and the scalar product is 1, and now I have a different vector, and I take the scalar product, and this gives 1, and you are asking if they differed by a phase. Be careful. I'm going to show you an example now. So we have seen that the polarization, the quantum state associated with polarization theta was described by cosine theta and sine theta as the entries of my vector. And now I claim, well, I can represent this quantum state using this representation here. So instead of writing cosine theta sine theta, I'm writing 1 over the square root of 2 exponential of minus I theta exponential of I theta. So this looks very different from the vector that we had before, right? But I'm saying that these must be the same quantum state that represents the quantum state of a photon polarized with polarization theta. So in order to do so, I can ask, what is the probability of... So now let me just answer Felix. So Felix, you see that this vector will have norm equals to 1. Okay? And this is not associated with the previous vector by just a phase. Actually, they are associated by what we call unitary transformations. But hold on, we are going to get there. Okay. Okay, so I have... okay, so I get the 1 over square root of 2 because this must be a normalized vector. Okay, so if I want to compute the norm of theta, okay, and I don't have the 1 over square root of 2, this will be the norm of this vector squared plus the norm of this vector squared. So sorry, not norm of the vector, norm of the component. So the norm of this component is 1. The norm of this component is 1. So if I sum them, this gives 2. But the vector must be normalized. So I have to multiply by 1 over square root of 2, so that when I square this number, this in total gives me 1. So I have 2 coming from here, and I'll have 1 over the square of square root of 2, which is 2. So 2 divided by 2 will give the norm 1 for the state vector theta. Did you understand? Why do I have to include the square root of 2? Okay, so there is still some question here, so let me phrase it differently. So assume that I tell you that my state vector, let me write it here, my state vector theta is actually a number A times E minus theta, E theta. So I don't know what is the value of A. So I want to compute the scalar product of theta with itself. And by postulate 1, this must be 1. Okay? So I just go to the definition of the scalar product. So what is the bra associated with this vector theta? The bra remember, you transpose and take the complex conjugate of the components. So there is a global factor A, so I have to take the complex conjugate of this global factor as well. So this will be A star. And the complex conjugate of e to the minus I theta is e to the I theta. And the complex conjugate of e to I theta is e to the minus I theta. So this is the bra associated with this cat. Okay? Now I will compute this. So when I compute this, I have to take the product between these two vectors here. Okay? So you see that I have a global factor, which is A star times A. A star times A is the norm of A squared. Okay. Now I have to take the product of this component with this component. So this is E I theta times E minus I theta. This gives E to the 0, which is 1. 1. And now I have the second component, which again will be exponential of minus I theta times exponential of I theta, which is also 1. Okay? In the end, this is giving to me 2 absolute value of A squared. So this is the norm of the vector, the norm squared of the vector theta. But by postulate 1, I know that this must be equal to 1. So I have to equate this to 1. As a consequence, let me continue here. Sorry for the mess. As a consequence, absolute value of A squared must be equal to 1 over 2. Okay? And now comes the question. So A is a complex number. So I'm looking for a complex number which has norm square equals to 1 over 2. But remember that I can always define a state up to some global phase. So I can choose a global phase in such a way that A is real. So if A is real, then A must be plus or minus 1 over square root of 2. Okay? So what I'm concluding is that the number that should multiply this factor should be plus or minus 1 over 2. 1 over square root of 2. That's the origin of this 1 over square root of 2. Is that clear now? Okay, good. Okay. Let me go back to the discussion here. So I'm saying that this state vector is associated with photon polarization theta. Well, if this is a way of describing the polarization, so my voice is, sorry. Can you hear me now? Oh. So I will turn off the video and see if it gets better. Can you hear me? So John says that he can hear. So okay, sorry about that. Okay. Let me check. So is it still too bad? So I will stop the record. Oh, so you're saying that now it's clear. Okay, okay. Then I think I will continue. Okay. So I'll keep the video turned off just for just to make sure that this is this will not make the connection too bad. Okay. Sorry about that. Okay, good. So now that if you start not getting what I say, please let me know. Okay, because then I can stop. Good. Now that I have defined these as being the quantum state associated with the photon polarization theta, I can compute what is the probability of getting, or the probability amplitude of getting photons polarized in the phi direction, given that they were prepared in the theta direction. So I take the bra associated with phi, and this will be, so if phi is defined as 1 over square root of 2 e to the minus I phi, e to I phi, then the bra will be 1 over square root of 2 e to the I phi, so I take the complex conjugate here, and the second entry will be e to the minus I phi, okay? And then I multiply by the ket associated with theta. That will just be the repetition of this vector here. So here is the ket. Okay? Now I have to compute that. So you see that I have 1 over square root of 2, 1 over square root of 2. The product of these numbers will give just 1 over 2. And now I have to compute the product of this row vector with this column vector. Okay? Just to be sure, are you hearing me well? Okay, okay, good. So computing now this product, so I have to take e to the I phi and multiply by e to the minus I theta and sum with e to the minus I phi times e to the I theta. So I have to take the product. There is a question. Can the entries of the ket for theta be square root of 1 over square root of 2 of the bra? So you are asking if I could change the sign here? So if the bra associated to phi is minus I phi plus I phi, is that what you're asking? No, you see that here there is this order. So if I'm using this basis of representation, I have to use these signs here. Okay. Okay. So you're saying that if I changed this e to the minus I theta to e to the I theta in the first component and also in the second component. So if I changed everybody, okay? Yes. Yes. Okay. Good. So yeah, so if you exchange that, then you're not going to change the scalar product. That's correct. Okay. So now if I take the product of this row vector with this column vector, I'm going to have these expressions here. 1 over 2 that comes from the product of the 1 over square root of 2 factors. And then I have exponential of I and then theta minus phi plus e to the minus I theta minus phi. So I have exponential of I times a number plus the exponential of minus I of the same number. So I have different signs in the exponential here. Okay? And remember that e to the I times an angle has this representation here. Okay? So if I sum e to the I theta with e to the minus I theta, I get 2 times cosine theta. Okay? So what you're going to obtain from this expression is the cosine of theta minus phi. If you don't understand immediately why this is equal to this, I invite you to rewrite this expression here using this expression here, and you're going to see that the signs will cancel out, and you're going to end up just with the cosine. Okay, but you see that this is nothing but the probability amplitude that we have obtained when we consider the state vector as being cosine of theta, sine of theta. So I'm not changing the probability amplitude by using this different representation. So you look at these vectors, this vector here, it's totally different from the one that we started the discussion. So it has complex numbers as entries, and but still, I'm not changing the physics if I use that. And the reason for that, there is a mathematical reason for that, of course, which is that you can change states by what we call, and we are going to discuss that later on, by what we call a unitary transformation without changing the probabilities. And this is something that should be similar to what you know from classical theory, that if you rotate your reference frame, you're not going to change the physics of it, right? So if you look to an apple falling in a one reference frame and you rotate, I guess I'm using too much my hands for the video to be off. Let me try to turn on the video. Let's see if it works. So can you still hear me well? Okay. So if you describe an apple falling and you are using a reference frame that is precisely that the vertical axis is aligned to the line of fall of the apple, and you just rotate the reference frame, of course, I mean, the coordinates of the apple will change, but you are not changing the fact that the apple will hit the floor at a given time. I mean, it will take some interval of time to hit the floor. So this is a physical prediction that you can measure, and this will not change if you just rotate the reference frame. Okay. Okay. That's good. I mean, you see that just to define what a state vector is, I had to talk about several different things. And this is something that you just get used by practicing. I mean, so if you just listen to me and don't try to, reproduce the arguments by yourselves, then this is not a thing that will naturally enters your brain. You have to really read and understand each step of the discussion. And as I said, there are some steps that you just have to swallow because these are rules that you have to obey in order to make physical predictions. Okay. Now I want to get to the second postulate. And in order to do so, I want to start a discussion. Okay, so there are two things that I want to discuss in this session, but I want to start with sorry, there is. I want to discuss some details about the measurements in quantum mechanics. Okay. Okay, so let me follow the discussion here. So when we were discussing photon polarization, we had that thing of saying that the photon was prepared in a state of polarization theta, and we were essentially measuring the probability that such a state would pass through a polarizer and change to a phi state. Okay, so what we are measuring is the polarization of the photon. But when you measure that, namely, has the photon passed through the polarizer and therefore has polarization phi, what you are asking is really a yes or no question. So if the photon crossed the polarizer, then you say yes, the photon crossed and now the polarization is phi. Or you answer no, the photon did not cross and the polarization, there is no photon with polarization phi. So the result is something like yes or no, okay, of this type of question. However, what we have seen is that you cannot tell for sure if the photon will pass or not through the polarizer. What you can tell is the probability that a photon will pass through the polarizer. And therefore, what happens is that you have to be careful, because if someone asks you, is the photon going to pass through the polarizer, you have to say, well, there is a chance of, and then you say the number, for the photon to pass. But we have seen that there is just one configuration that you are sure that the photon will pass. And this is a configuration which is when the polarizer is in the same direction as the photon polarization that you are throwing against the polarizer. So if you have a polarizer in the direction phi and your photons were prepared with polarization phi, then you know that all photons will pass through. But apart from that configuration, you don't know if the photon will pass through. You just know the probability that the photon will pass through. Okay? So for a generic polarization state, you cannot say with 100% of confidence if the photon will pass or not. You can just tell the probability of the outcome being yes or no. Okay, so this is different from classical mechanics, for instance, where, I mean, you have deterministic dynamics. You know what is going to happen with the system. You know what is the outcome given the initial conditions. In quantum mechanics, you don't know. In quantum mechanics, you tell the probability of something to happen. Okay? And just in very particular situations that you can ensure that the outcome will be a particular value or a particular property. Okay? So this is a very different way of understanding how you're going to make physical predictions. You predict now probabilities, and you don't say in a deterministic way what will be the value that you're going to measure. You can say, I will measure such a value with probability something. This is very different, okay? So with that, I will read the postulate 2, which says the following. If a photon is prepared in a polarization state A, the probability that it will be observed with polarization B after this binary observation, by binary observation I mean this observation of yes or no, is the probability of the photon being in polarization B if it is prepared with polarization A is the norm squared of this Dirac bracket. Okay? So if you have a state vector, an initial state vector A and a final state vector B, you can compute the probability by taking the Dirac bracket and taking the absolute value squared. This is a postulate, as I said. We saw that in the case of photon polarization, this is a natural thing, okay? Because you start with the interpretation using intensities of the electric magnetic waves, and then when you change the photon picture, this immediately gains the interpretation as the number of photons that is passing through the polarizer. But here, okay, I wrote the postulate still in the language of photon polarization, but again, this is a postulate that is generalized to other systems. So when I have a system in a given quantum state, and I want to measure if the system will have will be in a different quantum state, I have to take the Dirac bracket, take the absolute value and square. Okay. Let me check the questions. So why isn't the polarization state B written as bra? But so this is something that you should not confuse. What I'm measuring is if the photon will be in state B after the polarizer. So this is really a quantum state, so this is a cat. And what I'm saying is that in order to compute the probability, you have to use the bra. Okay? So this is as I said, I mean, if you have a cat, you can always translate it to a bra. So the property that this calculation is giving to me is the probability of a photon prepared in state A, so a cat A, will be observed in the state B, so cat B. And the postulate says that I have to take the bra B and multiply by the cat A, take the absolute value and square it. Okay? This is the postulate. So it's not, there is no meaning in write with polarization bra B, because the bra B is not the state vector. The bra B is the dual to the state vector B, which is a cat. Okay? Good. So the postulate now gives us a meaning why we need the normalization condition. So if I ask you, what is the probability of a photon to be polarized with polarization A if it was prepared with polarization A? What is the answer for that? Let me repeat the question. If I prepare a photon with polarization A, and I want to measure what are the chances of it being with polarization A after the polarizer, what is the, yeah. So if it is prepared with polarization A, and the polarizer has direction A, then the chances that I will see photons polarized with polarization A is 1. So if I replace B by A in this expression, this will be the absolute value of bra A, cat A, absolute value squared. But this is nothing but the absolute value squared of the first component of A plus the absolute value of the second component squared. And this must be equal to 1. Okay? That's why you need the normalization condition. Right? Otherwise, you're not going to get that all photons with polarization A will cross a polarizer with direction A. Okay? So you need the normalization. That's not just a convenient choice. Okay? There is another thing, which is the following. A probability is a number that is between 0 and 1, including 0 and 1. So you can have 0 chances of having some property, so this will be 0, and you can have 100% confidence that the system will have a given property, and this will give probability 1. So the probability must be between 0 and 1. So can we ensure that this number here is always between 0 and 1? Otherwise, it does not make sense as a probability. And in fact, you can show that this is the case by using the so-called Schwarz inequality. So if you take the absolute value squared of the scalar product between B and A, this must be less or equal than the absolute value squared of BB, absolute value squared of AA, but by postulate 1, these must be 1 and these must be 1. Okay? So the absolute value squared must be less or equal than 1. And we know that it must be bigger or equal than 0 because this is an absolute value. So you are summing, it's an absolute value squared. So you're summing two positive numbers or non-negative numbers, right? So this inequality ensures that you are dealing with a probability, namely a number between 0 and 1. All right? Is that clear? Okay. Okay, so the next thing that I want to discuss is circular polarization. So we are talking about linear polarization, so the electric field oscillates in a fixed direction. But I can have a circular polarization, namely the electric field oscillates, but it also rotates. So it is something like that. I mean, you have something that is oscillating and rotating. And you can also have photons circularly polarized. And I want to tell you how to describe that using photons. But I'm afraid that if I start now, it will be too short. Okay, so I think I will stop here. Otherwise, it is going to get too squeezed. And tomorrow we get to the circular polarization, and we continue with the discussion of the formalism of quantum mechanics. And tomorrow you have the quiz, so do not forget that. So I will proceed as the following. I will give the lecture, and we stop a bit earlier, and then you have the quiz. Okay? It's a short quiz, yeah. It is supposed to last up to 20 minutes. Okay. Okay, so I don't know how many questions. So the quiz will not be online. I will prepare it to be on paper. Okay. Not difficult one. No, it's not going to be difficult. You don't have to. I mean, if you're following the lectures, then it should be enough. So the topics covered by the quiz can be anything that I said so far since the first lecture. Okay. So it's really, but as I said, I'm not aiming at trapping you. So it's really to know if you are following the basic material. So you don't have to worry. If you are following the material, then you don't have to worry. So I don't want to make any particular comments about the type of questions because you know it's I think I mean it must be something that fits 20 minutes. So if you have to do a calculation, then it's not going to be a long calculation, and also not something that you need you know to use a computer or something. So it's something very simple. Okay. Okay, so I will stop recording. Thank you for your attention, and I'll see you tomorrow for lecture 10. Bye-bye.